26,000 light-years from here, space starts breaking its own rules. Stars race around an invisible monster at 5,000 miles per second. Time slows down. Radiation burns hot enough to vaporize metal. And at the very center sits something so massive, so dense, that not even light can escape once it gets too close. If you enjoy learning about the universe's darkest secrets, hit that like button and subscribe. We're heading straight into the heart of our galaxy, where the impossible becomes real. Take a breath. We're about to descend into the abyss. 50,000 light-years from the galactic center, something changes. You're still in what looks like normal space, stars scattered across darkness, familiar distances between them. But if you measure their velocity, the numbers don't add up. These stars are moving too fast, way too fast. In our neighborhood, stars orbit the galaxy at around 500,000 miles per hour, predictable, stable, following the same gravitational laws that keep Earth circling our home star. But here, those same laws start bending. Stars clock in at speeds that should fling them out into intergalactic space, never to return. The mass we can see doesn't explain it. Count up every star, every planet, every speck of dust in this region, and the gravity isn't strong enough to hold these stars in their orbits. They should have escaped billions of years ago. Yet, they haven't. They're locked in place by something we cannot see, dark matter, an invisible scaffolding that makes up 85% of all matter in the universe. We've never directly detected a single particle of it, but its gravitational fingerprints are everywhere. The closer you get to the galactic center, the denser this invisible framework becomes, and the faster it forces stars to move. Think about driving a car around a circular track. The tighter the turn, the faster you need to go to maintain your position. These stars are taking the tightest turn imaginable, held in orbit by a concentration of mass so enormous it warps space itself. The visible matter is just the tip of the iceberg. The real foundation lies hidden in the dark. Astronomers track these stellar velocities using redshift and blueshift. When a star moves away from us, its light stretches toward the red end of the spectrum. When it approaches, the light compresses toward blue. By measuring these shifts, we map their speeds with incredible precision, and the data reveals a pattern that shouldn't exist. The rotation curve stays flat. In a normal system, objects farther from the center should move slower, like planets in our solar system. But in galaxies, the speed stays constant or even increases with distance. This flatness proves something massive and invisible is pulling the strings. Measurements from dozens of galaxies show the same effect. The rotation curves don't drop off the way Newton's laws predict. Instead, they remain stubbornly flat, extending far beyond the visible edges of galaxies. Dark matter halos surround these systems, invisible but undeniably present. As you continue inward, those velocities keep climbing. What starts as slightly too fast becomes absurdly fast. Stars hurtling through space at millions of miles per hour, their orbits governed by forces we still don't fully understand. The mystery deepens with every measurement. But velocity is just the beginning, because once you cross this threshold, you start noticing something else, something that changes the nature of space itself. The darkness is disappearing. Move another 10,000 light-years closer, and night stops existing. In our part of the galaxy, stars are separated by vast gulfs of emptiness, light-years of nothing. You can pick out individual points of light against a black canvas. But here, near the galactic center, the canvas itself starts glowing. The stellar density increases by a factor of 100, then 1,000. Stars that would be separated by trillions of miles in our neighborhood now crowd together like cities on a map. The average distance between them shrinks from 4 light-years to less than 1 light-year. In some regions, it drops to mere light months. Imagine standing on a planet in this region. Look up at the sky, and you don't see scattered stars. You see a dome of light, thousands of stars bright enough to cast shadows, tens of thousands more, creating a background glow that never fades. The concept of darkness becomes meaningless. Your circadian rhythm would collapse. Life as we know it depends on the cycle of day and night, on darkness for rest and light for activity. But in the galactic center, there is no night. Just varying degrees of brightness. A planet here would be bathed in perpetual twilight, lit by the combined radiance of a stellar metropolis. The temperature never drops. On Earth, nighttime allows heat to radiate into space, cooling the surface. But with constant stellar radiation from all directions, any planet here would bake under an endless heat source. Atmospheric temperatures would stabilize at levels that make complex life nearly impossible. Photosynthesis would go haywire. Plants on Earth have evolved to respond to day-night cycles, using darkness as a signal to regulate growth and reproduction. Remove that signal, and you remove one of the fundamental timekeepers of biology. Constant light means constant energy input, but also constant stress on living systems that evolved for alternating conditions. Navigation becomes trivial and impossible at the same time. Trivial because you have thousands of bright reference points to guide you. Impossible because those reference points move so fast and crowd so densely that creating stable star charts is a nightmare. Constellations shift on timescales of centuries instead of millennia. The sky doesn't just glow with visible light. Infrared radiation floods the region, invisible to human eyes but detectable by instruments. Every star pumps out heat along with light, and with so many stars packed together, the ambient temperature of space itself rises above the cosmic background radiation. Even the vacuum starts warming up. This density creates stellar encounters. Not collisions yet, but close passes where stars swing past each other, their gravity briefly interacting. These encounters can fling planets out of orbit, steal comets from neighboring systems, or send asteroids careening into new trajectories. The gravitational chaos increases with every light year you descend. The night sky, we know, that black velvet backdrop with tiny diamonds of light, is a luxury of living in the galactic suburbs, a privilege of distance and isolation. Here, you're moving into downtown, and downtown has a problem that goes far beyond too many stars. Gravity stops being gentle. You've traveled deeper into the galactic center, and now the forces acting on you start doing things they shouldn't. Not just pulling you in one direction, but pulling different parts of you in different directions, strong enough to matter, strong enough to destroy. This is called tidal force. The same principle that causes ocean tides on Earth, but amplified to cosmic extremes. Earth's oceans bulge toward the moon because the near side experiences slightly more gravitational pull than the far side. That tiny difference creates the tides. Here, that difference becomes enormous. Imagine a spacecraft 100 feet long. The front end sits closer to the galactic center than the back end. In normal space, that difference is negligible. But as you approach the region where gravity dominates, that 100-foot gap means the front experiences measurably more pull than the back. The ship starts stretching. At first, it's subtle. Structural stress. Metal groaning under forces it wasn't designed to handle. Engineers hear creaks and pings as hull plates shift. Instruments detect microfractures forming in critical supports, but keep moving inward and those forces multiply. The front accelerates faster than the back. The gap widens. What was solid metal becomes taffy being pulled apart. This doesn't just affect spacecraft. Asteroids entering this region begin elongating. Small moons orbiting too close to massive bodies get stretched into egg shapes, then into ellipsoids, then into streams of rubble. The Roche limit is the boundary where tidal forces overcome an object's own gravity, cross it, and the object disintegrates. Gas clouds feel it too. Molecular clouds that might be spherical in the outer galaxy become stretched into long filaments near the center. These filaments can span hundreds of light years, pulled into thin strands by the competing gravitational forces of multiple massive objects. The clouds look like cosmic hair, streaming toward the center. Even light gets affected. Photons traveling through regions of strong tidal forces experience something called gravitational shear. Their paths bend differently, depending on which part of the gravitational field they pass through. This creates distortions in the images we see, stretching and warping distant objects like looking through a funhouse mirror. For a human body, the effect would be catastrophic long before you reached the center. Your feet, closer to the source of gravity, would be pulled harder than your head. The difference would rip you apart at the molecular level. Astronomers call this spaghettification, and it's exactly as violent as it sounds. Your body would be transformed into a long, thin stream of atoms. The violence escalates. Tidal heating occurs when an object gets repeatedly stretched and squeezed by varying gravitational forces. This friction generates heat. Moons orbiting gas giants experience this, keeping their interiors molten. But near the galactic center, tidal heating can melt rock, vaporize ice, and turn solid matter into plasma. Differential rotation adds another layer of chaos. Objects in orbit closer to the center move faster than those farther out. This shearing motion creates turbulence in gas clouds, stirring them into complex, chaotic patterns. What should be smooth flows become violent eddies and whirlpools of matter. The tidal forces you're experiencing now are just a preview, because as you push deeper into this region, another threat emerges, one that doesn't just stretch matter, it burns it. Space becomes hostile in a new way. You're still thousands of light years from the galactic center, but the radiation levels are already climbing. Not the gentle cosmic background radiation that pervades the universe. Not the solar wind from a single star. This is a storm of high-energy particles and electromagnetic waves that would kill you in seconds without protection. X-rays flood the region, generated by superheated gas swirling around compact objects like neutron stars and black holes. These X-rays carry enough energy to strip electrons from atoms, ionizing matter on contact. A human body exposed to this radiation would absorb doses measured in thousands of grays per hour. 10 grays is lethal. Thousands would cook you from the inside out. Gamma rays join the assault, the highest energy photons in the universe, created by the most violent processes imaginable. Stellar explosions, particle collisions near black holes, matter-antimatter annihilation. Each gamma-ray photon carries more than 1,000,000 times the energy of visible light. They pass through most materials like they're not even there, leaving trails of destroyed molecules in their wake. Cosmic rays add to the bombardment. These aren't rays at all, but high-speed atomic nuclei accelerated to nearly the speed of light. Protons, helium nuclei, even heavier elements, all moving fast enough to shatter whatever they hit. When a cosmic ray strikes DNA, it doesn't just damage it. It obliterates entire sections of genetic code, leaving cells unable to repair themselves. The density of these particles increases as you approach the center. In our neighborhood, you might encounter one high-energy cosmic ray per square centimeter per second. Here, that number jumps to hundreds, then thousands. The space between stars becomes a shooting gallery of deadly particles. Shielding becomes the difference between life and death. Synchrotron radiation creates a continuous glow across the electromagnetic spectrum. Electrons spiraling in magnetic fields emit this radiation as they accelerate. The stronger the magnetic field, the more intense the emission. And near the galactic center, magnetic fields reach strengths that would tear ordinary matter apart. Spacecraft shielding becomes inadequate. The materials that protect astronauts in Earth orbit, or even on a trip to Mars, would be overwhelmed in minutes here. Lead walls several feet thick might buy you hours. But eventually, the radiation finds its way through. It always does. Living tissue fares even worse. Cells rely on precise chemical reactions, on delicate protein structures, on DNA that must remain intact to function. High-energy radiation disrupts all of this. Proteins unfold and denature. DNA strands break apart. Cell membranes rupture. Even if you survived the immediate exposure, the damage accumulates. Cancer, organ failure, genetic mutations that would render any offspring non-viable. The radiation doesn't just come from external sources. As particles slam into spacecraft hulls, they create secondary radiation, neutrons, smaller fragments, a cascade of destruction that multiplies the danger. What starts as one cosmic ray hitting a metal wall becomes a dozen particles spraying into the interior. Temperature spikes from the constant energy input. Unlike the slow heating from stellar light, this is immediate and penetrating. Materials absorb radiation and convert it to heat. Electronics fail as components overheat. But this radiation serves a purpose beyond destruction. It illuminates. It reveals structures that would otherwise remain hidden in the darkness. Structures so vast and so hot, they reshape our understanding of what's possible. And as you press forward, those structures begin to emerge from the data. Your clock starts lying to you. Not broken, not malfunctioning, just running slower than it should. Compared to a clock back on Earth, yours falls behind. Seconds stretch into slightly longer seconds. Minutes expand. And the deeper you travel into the galactic center's gravitational well, the worse it gets. This is gravitational time dilation, predicted by Einstein over a century ago and confirmed by every precise measurement we've ever made. Time is not absolute. It bends and stretches in the presence of mass and energy. The stronger the gravity, the slower time flows. On Earth's surface, you experience a tiny amount of this effect. Clocks at sea level run slightly slower than identical clocks on mountaintops. The difference is measured in nanoseconds, imperceptible to human senses but real enough to require corrections in GPS satellites. Without accounting for time dilation, your navigation would drift miles off course within hours. But Earth's gravity is weak compared to what you're experiencing now. The supermassive black hole at the galactic center warps spacetime so severely that time dilation becomes impossible to ignore. A clock near the center ticks measurably slower than one in our solar neighborhood. Imagine two twins. One stays on Earth, the other travels to the galactic center and hovers there for what feels like 10 years by their clock. When they return, they've aged 10 years. But their Earth-bound twin has aged 11 years, or 12, or more, depending on how close to the center they got. Time didn't just pass differently for them, it passed at genuinely different rates. This affects more than clocks. Chemical reactions slow down. Radioactive decay takes longer. Biological processes that depend on precise timing get thrown off. Light waves stretch to longer wavelengths as they climb out of the gravitational well, losing energy in the process. This gravitational redshift adds to the redshift from velocity, making objects near the center appear even more shifted toward the red end of the spectrum. Communication becomes a nightmare. Send a radio signal from near the center back to Earth, and it arrives at a lower frequency than it was transmitted. The message takes longer to receive, not just because of distance, but because time itself is running at different speeds at the two locations. Coordinate a rendezvous, and you have to account for the fact that your partner's clock is not synchronized with yours in any absolute sense. Orbital mechanics get weird. Objects orbiting in strong gravitational fields don't follow simple ellipses. Their orbits precess, with the point of closest approach slowly rotating around the central mass. Mercury does this around our home star, its orbit shifting by 43 arcseconds per century, a discrepancy that stumped astronomers until Einstein's equations explained it perfectly. Near the galactic center, that precession amplifies. Orbits twist and rotate on timescales of years instead of centuries. Predicting where an object will be requires accounting for relativistic effects that Newton's laws ignore completely. The mathematics become complex, involving tensor calculations that would fill entire textbooks. The psychological impact would be profound. Knowing that every moment you spend near the center costs you more time than it costs people back home. Every decision carries weight. Stay too long, and you return to a future where everyone you knew is older or gone. The universe has moved on while you were frozen in slower time. But time dilation is just one way gravity warps reality here, because the orbits themselves are about to show you something that defies every expectation you brought from the orderly regions of space. The stars stop playing by the rules. Back in our solar neighborhood, orbits make sense. Planets circle our home star in roughly the same plane, like a flat disk. The galaxy as a whole rotates like a pinwheel, stars moving in orderly circles around the center. Everything aligned, everything predictable. Astronomers can calculate positions centuries into the future. Here, that order collapses. Stars orbit at wild angles to each other. Some circle in one plane, others tilt 30 degrees off that plane. Some go perpendicular. A few even orbit retrograde, moving in the opposite direction from the majority. It's chaos, but chaos with a cause. These orbits tell a story of violence. When stars form in a calm, rotating cloud of gas, they inherit that rotation. They orbit in the same direction, in the same plane, because that's the configuration that conserves angular momentum. But when stars form from turbulent, colliding gas streams, or when they get scattered by gravitational encounters, all bets are off. The galactic center is a battleground. Gas clouds slam into each other at thousands of miles per second. Shock waves trigger star formation in bursts, creating clusters that don't share a common rotation. These newborn stars then interact gravitatically, flinging each other into tilted orbits through a process called gravitational scattering. Binary stars make it worse. When two stars orbit each other, their combined gravity affects nearby objects differently than a single star would. A third star passing too close can get caught in a chaotic three-body interaction, emerging on a wildly different trajectory. Do this billions of times over millions of years, and you scramble the orbital planes beyond recognition. The central black hole acts like a cosmic stirring rod. Its gravity dominates everything within a certain radius, and stars orbiting it don't follow the same rules as stars orbiting farther out. The massive object's influence creates a distinct population of stars with orbits that range from nearly circular to extremely elongated ellipses, all jumbled together in orientation. Measuring these orbits requires decades of patient observation. Astronomers take images year after year, tracking each star's position against the background. Plot those positions over time, and the orbital paths emerge. Some stars complete their orbits in a human lifetime, others take centuries. But the patterns reveal the mass distribution, the history of interactions, and the gravitational architecture of the region. One group of stars, called the stars, orbits so close to the central black hole that their velocities reach a significant fraction of light speed. These stars complete orbits in years or decades, moving so fast they blur in images taken months apart. Their paths are tilted at random angles, each one a rosette pattern precessing around the gravitational anchor. The tilted orbits create another problem for any civilization trying to navigate this region. There's no single reference plane, no galactic north or south that makes sense. Every direction is as valid as any other. Star charts become three-dimensional puzzles where orientations matter as much as distances. And the density of stars in these tilted orbits means close encounters happen with disturbing frequency. Not collisions yet, but near misses where stars pass within light months of each other. This randomness hides structure. Because underneath the visible chaos, there's an invisible framework shaping everything. You can't see the galactic center, not with human eyes. Between Earth and the center lies a wall of dust. Trillions upon trillions of tiny particles, each smaller than a grain of sand, scattered across 26,000 light-years of space. They block visible light almost completely. Point the most powerful optical telescope at the galactic center, and you see nothing but darkness. But switch to infrared, and the darkness explodes with light. Dust absorbs visible and ultraviolet light from stars, heating up to a few hundred degrees above absolute zero. At that temperature, it glows in infrared wavelengths, invisible to human eyes, but blazingly bright to specialized detectors. What was black becomes a tapestry of glowing filaments, bubbles, and clouds. The transformation is complete. The James Webb Space Telescope sees this region in stunning detail. Structures hidden for millennia reveal themselves, dense knots of dust where new stars are forming, shock fronts where gas clouds collide at thousands of miles per second, cavities carved by stellar winds and supernova explosions. Every feature tells a story of processes happening behind the veil. Infrared penetrates where visible light cannot. Those dust grains that block optical photons let longer wavelength infrared pass through with only moderate absorption. The deeper the infrared, the less the dust matters. At wavelengths of 10 to 20 microns, we can peer straight through the galactic plane to the center beyond. What we see there defies simple description. A region called Sagittarius A spans hundreds of light years, packed with gas and dust at temperatures ranging from tens to thousands of degrees. Radio emissions from ionized gas, infrared glow from heated dust, X-rays from matter being torn apart by extreme gravity, all overlapping in the same space, creating a multi-wavelength symphony. The dust itself comes from dying stars. Red giants shed their outer layers in stellar winds, releasing gas and dust into space at rates of 1/10,000th of a solar mass per year. Supernovae explode, forging heavy elements and blasting them into the interstellar medium at velocities exceeding 10,000 miles per second. Over billions of years, these processes enrich the galactic center with metals, silicon, carbon, oxygen, all the raw materials for planets and life. But this enrichment comes with a cost. The dust dims everything. Stars that should be bright appear faint. Distances become harder to measure. Spectroscopy, the technique of analyzing light to determine composition and properties, gets complicated by the dust's interference. Photons get scattered, absorbed, and re-emitted, scrambling the information they carry. Some dust clouds organize into long filaments aligned with magnetic fields. These filaments stretch for light years, tracing the invisible magnetic architecture of the galactic center. The fields channel charged particles, guide flows of gas, and shape the distribution of matter in ways gravity alone cannot. They create order within the chaos. Infrared surveys have mapped thousands of these structures. Some are cold and dark, barely above the temperature of space itself. Others are warm, heated by nearby stars or embedded protostars. Beneath the infrared glow, something else lurks. Magnetic fields strong enough to shape the cosmos. Magnetism reaches strengths that should not exist. In our solar neighborhood, magnetic fields are weak. Earth's magnetic field protects us from solar wind, but it's gentle enough that a child's toy magnet can overpower it locally. Even the strongest magnets we can build in laboratories reach maybe 50 Tesla, powerful but tame compared to what exists near the galactic center. Magnetars change the rules. These neutron stars, each only 12 miles across, generate magnetic fields a quadrillion times stronger than Earth's. 10 billion Tesla. At that strength, magnetism stops being a minor player and becomes a fundamental force reshaping reality. The physics textbooks need rewriting. Light bends in magnetar fields. Photons traveling through such intense magnetism don't move in straight lines anymore. They curve, their polarization rotates, and they can even split into multiple paths depending on their orientation. This effect, called vacuum birefringence, turns empty space into something like a crystal with different properties in different directions. atoms get stretched. Normally, atoms are spherical, with electrons orbiting in clouds around the nucleus. But in magnetar fields, those clouds elongate into cigar shapes, aligned with the field lines. The stronger the field, the more extreme the distortion. At the surface of a magnetar, atoms become so deformed they barely resemble their field-free forms. Matter itself becomes directional. Materials that would be isotropic in weak fields develop strong preferences for alignment. Molecular bonds strengthen in one direction and weaken in others. Crystals form with bizarre lattice structures, optimized to minimize magnetic energy rather than chemical energy. The usual rules of chemistry no longer apply. These fields don't just affect matter, they affect spacetime. General relativity tells us that energy curves space, and magnetic fields contain energy. A magnetar's field is so energetic that it contributes measurably to the star's total mass energy, adding to its gravitational pull. The field literally weighs something. You could measure its mass on a scale if you had a scale that could survive. Magnetars release their energy in bursts. When the crust of a magnetar cracks under magnetic stress, it triggers a starquake that reorganizes the field. The sudden rearrangement releases energy equivalent to what our home star emits in 100,000 years, all in less than a second. These bursts flood the surrounding space with gamma rays and X-rays. Near the galactic center, several magnetars have been identified. Each one is a ticking time bomb of magnetic energy. When they flare, they briefly outshine everything else in the region. Satellites across the galaxy detect the flash. Any spacecraft caught in the direct path of the burst would be fried instantly, its electronics reduced to molten slag. The magnetic fields also accelerate particles to incredible energies. Charged particles spiraling in these fields gain energy with each orbit, reaching velocities approaching light speed. These particles then escape into space as cosmic rays, some of the highest energy particles ever detected. They bombard Earth from all directions, remnants of magnetar violence. Magnetic reconnection adds another layer of chaos. When magnetic field lines with opposite orientations come close together, they can snap and reconnect in a new configuration. This process converts magnetic energy into kinetic energy and heat explosively. But magnetars are just one source of magnetic turmoil here. The entire galactic center seethes with tangled, amplified fields that do more than bend light. They accelerate gas clouds to impossible speeds. Matter stops behaving like matter. You watch a cloud of gas the size of several solar systems racing toward the galactic center at 2,000 miles per second. That's almost 1% of the speed of light. At those velocities, relativistic effects kick in. The cloud's mass increases, according to Einstein's equations. Time dilates. Collisions with stationary gas generate shocks hot enough to emit X-rays. This isn't gentle drift. This is acceleration driven by gravity so intense it overwhelms every other force. The central black hole pulls, and the cloud responds like a satellite in freefall. Except there's no orbit stable enough to save it. It's diving in, and nothing can stop it. The trajectory is sealed. The cloud heats up as it accelerates. Friction with surrounding gas converts kinetic energy into thermal energy at a furious rate. What starts as a relatively cool molecular cloud at a few hundred degrees becomes a glowing plasma at millions of degrees. Atoms ionize. Electrons rip free from nuclei. The cloud becomes a river of charged particles, flowing inexorably inward. Shock waves form at the leading edge. When the fast-moving cloud slams into slower gas ahead of it, the collision creates a discontinuity in pressure, density, and temperature. The shock front radiates energy across the electromagnetic spectrum: radio waves from accelerated electrons, infrared from heated dust, visible light from ionized hydrogen, X-rays from the hottest regions where temperatures exceed 10 million degrees. Some clouds survive the journey, They're dense enough and compact enough that tidal forces don't rip them apart immediately. These survivors plunge deep into the gravitational well, reaching within light years of the black hole before either being captured into orbit or shredded by tidal stress. Astronomers have tracked several of these clouds, watching them evolve over years as they approach the center. One cloud, designated G2, became famous for its close encounter. Predictions suggested it would be torn apart in a spectacular display of accretion and flaring. Telescopes around the world watched as it made its closest approach in 2014. The cloud survived, elongated and heated, but intact enough to continue its orbit. The expected fireworks didn't happen, surprising researchers who had anticipated a dramatic light show. The survival raised questions. How dense must a cloud be to resist tidal shredding? What's the internal structure that keeps it together? Is there something hidden inside? A star or a compact object providing gravitational glue? The mystery remains partially unsolved. Other clouds aren't so lucky. They disintegrate into streams of gas that spiral inward. These streams feed the black hole, adding to the accretion disk and fueling the region's high-energy emissions. Each infalling cloud contributes a tiny fraction of its mass to the black hole's growth, a process that's been ongoing for billions of years. The velocities involved create Doppler shifts, so large they're easy to measure. Gas moving toward us appears blue-shifted, its spectral lines shifted to shorter wavelengths. Gas moving away appears red-shifted. By mapping these shifts across a cloud, astronomers reconstruct its three-dimensional velocity structure, revealing rotation, expansion, and bulk motion. Turbulence dominates the flow. Instead of smooth, laminar motion, the gas churns in eddies and vortices. Magnetic fields add to the chaos. These clouds aren't just passive victims. When they collide with each other, they trigger shock-induced star formation. When they fall into the black hole, they power the very emissions we use to study the region. And speaking of collisions, you're about to witness something that happens here with disturbing regularity. Stars crashing into each other. Two stars collide. Not near misses. Not gravitational encounters that deflect orbits. Actual physical collisions where stellar atmospheres merge, plasma mixes, and fusion reactions go haywire. Events so violent, they briefly outshine entire galaxies. And in the dense stellar environment near the galactic center, they happen with the frequency of car crashes on a busy highway. Run the numbers. In our solar neighborhood, the average distance between stars is about 4 light years. Stars move at typical speeds of a few 100,000 miles per hour. Given their small size compared to the vast spaces between them, stellar collisions are vanishingly rare. The expected time between collisions in our region is longer than the current age of the universe. But near the galactic center, those numbers change dramatically. The average separation drops to less than 1 light year in the densest regions. Stellar velocities increase to millions of miles per hour, and the sheer number of stars per unit volume skyrockets. Suddenly, collisions shift from impossible to inevitable. The math is brutal. Collision rate scales with stellar density squared and with velocity. Double the density, quadruple the collision rate, increase the velocity, more collisions per unit time. In the nuclear star cluster surrounding the central black hole, the collision rate is estimated at 1 every 10,000 to 100,000 years. That might still sound rare, but on cosmic timescales, it's frequent. Over the billions of years the galaxy has existed, millions of stellar collisions have occurred in this region, each one reshaping the stellar population, each one releasing energy that affects the surrounding environment. What happens during a collision depends on the stars involved. Two low-mass stars, meeting at low relative velocity, might merge gently, forming a single bloated star with a mixed composition. The merger spins up the combined star, potentially creating a rapidly rotating object that evolves differently than stars born through normal processes. High-velocity collisions are more violent. When stars slam together at thousands of miles per second, the impact generates shock waves that compress and heat the stellar material. Temperatures spike to hundreds of millions of degrees. Fusion reactions that normally occur only in stellar cores ignite in the collision zone. The stars don't merge smoothly, they explode partially, shedding mass in all directions. These collisions can trigger supernovae. If one of the colliding stars is a white dwarf, the impact might add enough mass to push it over the Chandrasekhar limit, the threshold where electron degeneracy pressure fails. The collapse detonates a type Ia supernova, an explosion bright enough to see across the universe. Even without triggering supernovae, collisions eject material. Stellar atmospheres get stripped away by the violence of impact. This debris enriches the interstellar medium with heavy elements, contributing to the chemical evolution of the galactic center. Some collisions produce exotic objects. Blue stragglers, stars that appear younger and bluer than their neighbors, likely form through stellar mergers. These objects stand out in star clusters as anomalies that don't fit standard evolutionary models. Their existence points to a history of violent interactions. Binary stars complicate the picture further. If one star in a binary collides with a third intruder, the result can be a stable triple system, an ejected star, or the destruction of the original binary. The collision rate increases dramatically close to the central black hole. Stars in tight orbits move even faster and crowd even closer together. Their orbits precess and tilt, ensuring that intersections occur regularly. Detecting these collisions from Earth is challenging. The events are brief, lasting hours to days. By the time we notice a brightening, the collision may already be over. And within that medium, in the oldest, densest region of all, something even stranger waits. You've entered the nuclear star cluster. This is where the galaxy's oldest residents gather. A sphere of stars 10 light-years across, centered on the supermassive black hole. More than 25 million stars packed into a volume that would barely contain a handful in our neighborhood. The stellar density here exceeds anything else in the galaxy by orders of magnitude. These aren't young, hot stars. Most are ancient red giants and evolved stars that have been orbiting the galactic center for billions of years. They've survived countless gravitational encounters, avoided collisions, and endured the harsh radiation environment. The survivors of a brutal cosmic sorting process that has eliminated the weak. The cluster formed early in the galaxy's history. When the Milky Way was young, gas and dust concentrated toward the center, triggering intense star formation in massive bursts. Those early stars evolved, died, and were replaced by new generations. But some of the oldest ones remain, fossils from an era when the galaxy looked completely different. Measuring the ages of these stars reveals galactic history. The chemical composition of a star reflects the composition of the gas cloud it formed from. Older stars contain fewer heavy elements because those elements hadn't been produced yet by earlier generations of stars. The nuclear star cluster contains a mix of ages, from ancient metal-poor stars to relatively young metal-rich ones. The distribution of stars within the cluster follows a pattern. Density increases toward the center, peaking at values around 100 million stars per cubic light-year near the black hole. That's 1 million times denser than our solar neighborhood. At those densities, the average distance between stars drops to light weeks. In some extreme pockets, it's measured in light days. Imagine standing on a planet in this environment. The night sky would be unrecognizable. Stars would appear as a continuous glow, individual points blending together into a luminous fog. The combined light from millions of nearby stars would be bright enough to read by, casting multiple overlapping shadows from every object. The cluster's gravitational potential is dominated by the central black hole, but the collective mass of millions of stars still matters. This creates a cusp in the density profile, a sharp increase in stellar concentration as you approach the center. Theoretical models predict this cusp, and observations confirm it exists. Stars in the cluster move fast. orbital velocities range from hundreds to thousands of miles per second. These speeds result from the intense gravity of the central black hole and the cluster's own mass. The faster a star moves, the less time it spends in any given location, which affects how we observe and count stars in different regions. The cluster is not static. Stars enter and leave through dynamical processes. A star passing through the cluster can be captured by a close encounter that saps its energy, trapping it in orbit around the center. Conversely, a star can gain energy from an encounter and be ejected, flung out of the cluster at high velocity. These ejections create hypervelocity stars, stars moving so fast they'll eventually escape the galaxy entirely, traveling through intergalactic space at speeds exceeding 1,000 miles per second. Astronomers have detected dozens of these runaways, tracing their paths backward to origins near the galactic center. Each one tells a story of a violent gravitational slingshot. The nuclear star cluster also contains exotic objects, millisecond pulsars spinning hundreds of times per second, X-ray binaries where a normal star feeds material onto a neutron star or black hole, Wolf-Rayet, stars shedding mass at prodigious rates. But all of these objects, living and dead, orbit the same central point, the gravitational anchor that holds the entire cluster together. And that anchor is about to reveal itself. There it is, Sagittarius A*, pronounced Sagittarius A star, the monster at the heart of our galaxy, 4 million times the mass of our home star, compressed into a region smaller than Mercury's orbit, the gravitational anchor around which everything else revolves. You can't see it directly. Black holes don't emit light. They're defined by the absence of light, by the event horizon beyond which nothing escapes. But you can see its effects. The way stars orbit around empty space, the way gas clouds accelerate as they approach, the way radio waves and X-rays emerge from the surrounding accretion flow. The evidence for this object is overwhelming. Decades of observations tracking individual stars near the galactic center reveal their orbits precisely. These orbits follow Kepler's laws perfectly, allowing astronomers to calculate the mass of the object they're orbiting. The answer always comes back the same: 4 million solar masses, concentrated in a volume no larger than a few light-hours across. No other object fits the data. A cluster of dark stars would create different orbital dynamics. A giant ball of dark matter would be too diffuse. Only a black hole provides the right combination of mass and compactness to explain what we observe. The black hole sits at the exact center of the galaxy, not approximately at the center, exactly. This isn't coincidence. The black hole and the galaxy grew together, each influencing the other's evolution over billions of years. As the galaxy formed and matter fell toward the center, some of that matter fed the growing black hole. The black hole's gravity shaped the distribution of stars and gas around it. This relationship between black holes and galaxies appears universal. Nearly every large galaxy contains a supermassive black hole at its center. The mass of the black hole correlates with properties of the galaxy, like the velocity dispersion of stars in the central bulge. Bigger galaxies have bigger black holes, suggesting they evolved together through cosmic history. The central black hole is relatively quiet compared to its cousins in other galaxies. Many galactic centers are active, with black holes accreting matter at prodigious rates and blasting out jets of plasma at nearly light speed. This one accretes slowly, pulling in only a tiny trickle of gas. This makes it faint compared to active galactic nuclei, but it also makes it easier to study the region around it without being blinded by intense radiation. The radio emission comes from synchrotron radiation in the accretion flow. Hot gas spiraling toward the black hole emits radio waves as electrons accelerate in magnetic fields. The emission is variable, flickering on timescales of minutes to hours as turbulence in the accretion flow changes the conditions. X-rays flare occasionally. When a clump of gas falls in, it heats up to extreme temperatures and radiates X-rays before crossing the event horizon. These flares are unpredictable, sometimes bright enough to be detected by space-based X-ray telescopes. Infrared observations reveal stars orbiting incredibly close. The closest approach distances measured in light hours, not light years. At those separations, the stars experience gravitational forces that would tear planets apart. The mass continues to grow, but slowly. At current accretion rates, it would take trillions of years to double its mass. But the black hole's mass is just one property. Its size, defined by the event horizon, is even more staggering, and some stars orbit so close they graze that boundary. The stars are doing the impossible. In our solar system, Earth takes 1 year to orbit our home star. Neptune, at the outer edge, takes 165 years. Even Pluto, in its elongated path, requires 248 years to complete one circuit. These are the timescales we're used to for orbital motion around massive objects. Near the galactic center, those timescales collapse. Star S2, also called S0-2, completes its orbit in 16 years, 16, one human generation. Astronomers discovered this star in the early 1990s and have now watched it complete more than 2 full orbits. They've tracked its position year after year, plotting its elliptical path with extraordinary precision. Every data point confirms the theories. At its farthest point from the black hole, S2 sits about 1,000 astronomical units away. That's roughly 25 times Neptune's distance from our home star. Not particularly close on cosmic scales, but at its nearest approach, called periastron, S2 plunges to just 120 astronomical units from the black hole's event horizon. That's closer to the central monster than Earth is to our home star. And the black hole contains 4 million times more mass. The velocity S2 reaches during periastron is mind-bending. 5,000 miles per second, almost 3% of the speed of light. At that speed, you could travel from Earth to the Moon in less than 50 seconds. Relativistic effects become significant. Time dilation, gravitational redshift. The star's motion tests Einstein's general relativity in ways impossible anywhere else. Observations of S2's orbit have confirmed general relativity predictions with incredible precision. The orbit precesses, with the point of closest approach rotating around the black hole by about 12 arc-minutes per orbit. This Schwarzschild precession results from the curvature of spacetime near the black hole, an effect completely absent in Newtonian gravity. The star's light gets redshifted as it climbs out of the gravitational well. During periastron, photons lose energy fighting against the black hole's gravity. When S2 is at its closest, its spectral lines shift toward longer wavelengths by amounts perfectly matching general relativity's predictions. Newton's laws would predict no such shift. Other stars orbit even faster. S4714 holds the current record for the shortest known orbital period, 12 years. Its velocity at periastron reaches 8% of light speed. At those speeds, the star experiences time dilation measurable with current instruments. These orbits aren't stable forever. Over millions of years, gravitational interactions with other stars will perturb them. Some stars will be scattered onto wider orbits. Others might be flung out of the system entirely. A few unlucky ones could be pushed onto trajectories that send them spiraling into the black hole. The stars are massive, hot, young stars. Most are blue giants with masses 10 to 20 times that of our home star. They shouldn't exist this close to such an extreme environment. Stars don't form in such conditions. The tidal forces and radiation would disrupt any protostellar cloud trying to collapse. So, how did they get there? One theory suggests they formed farther out in a binary system. The binary wandered too close, which captured one star and ejected the other. The captured star settled into a tight orbit, becoming a star. Another theory proposes the stars formed in a massive accretion disk billions of years ago. The disk was dense and cool enough for star formation. After the stars formed, the disk dissipated. Either way, these stars exist on borrowed time. Eventually, they'll exhaust their nuclear fuel and explode as supernovae. But one star ventures even closer than S2, close enough to test the absolute limits of what's possible near a black hole. S62 rewrites the rules. Discovered in 2019, this star orbits closer to the central black hole than any other known object. Its periastron distance is a mere 16 light-hours from the event horizon. For comparison, that's roughly the distance from our home star to Uranus, except here, you're that close to a monster 4 million times more massive. The orbital period is 9.9 years, less than a decade to complete one full orbit around the supermassive black hole. Every 9.9 years, S62 makes its death-defying plunge toward the event horizon, accelerates to insane velocities, and swings back out to safety. It's a cosmic dance performed on the edge of oblivion. During that closest approach, S62 reaches velocities exceeding 6,000 miles per second. That's more than 3% of light speed. Relativistic mechanics dominate. The star's mass increases measurably due to its velocity. Time aboard, the star runs slower than time in the surrounding space. Light leaving the star gets redshifted by the combined effects of gravity and motion. The gravitational forces at periastron are extreme. Tidal forces try to stretch the star along its orbital path while compressing it perpendicular to that path. S62 is massive enough and compact enough to resist this tidal stress, but smaller objects would be torn apart. The Roche limit lies closer to the black hole than S62's periastron, but not by much. The orbital eccentricity is high. S62 follows an extremely elongated ellipse, spending most of its time far from the black hole and only brief periods at close approach. This high eccentricity suggests a violent history. Something scattered S62 onto this orbit, possibly a gravitational encounter with another star or a close passage by the black hole that captured it. Observations of S62 provide unprecedented tests of general relativity. The combination of high velocity and strong gravitational field creates conditions where relativistic effects are large and measurable. Every measurement confirms Einstein's predictions. The orbit precesses, light gets redshifted, time dilates. Everything matches theoretical expectations to within the measurement uncertainties. But S62 also reveals how little we know. The star's proximity to the black hole means it samples regions of spacetime we can barely probe with other methods. Any deviation from general relativity would show up first in S62's orbit. So far, no deviations have been detected, but the precision continues improving with each observational campaign. The discovery of S62 suggests more stars might orbit even closer. Detection bias favors finding brighter, farther stars. Faint stars on very tight orbits might exist but remain hidden in the glare of the galactic center. Deeper surveys with more sensitive instruments could reveal a whole population of objects pushing even closer to the black hole. How close can a star get and survive? The theoretical limit depends on the star's density and tidal forces. Main sequence stars, like our home star, would be destroyed several light-hours out. But compact objects like white dwarfs or neutron stars could survive much closer, potentially within light minutes of the event horizon. S62's orbit will eventually decay. Gravitational wave emission, though tiny, slowly drains energy from the system. Over millions of years, the orbit shrinks. Eventually, S62 will either be scattered onto a different path by interactions with other stars, or it will spiral inward and cross the event horizon. When S62 finally falls in, it will contribute a tiny fraction of its mass to the black hole. the monster barely notices. And that horizon, the boundary between existence and oblivion, is larger than most people realize. The point of no return spans 14 million miles. That's the diameter of the event horizon around the central black hole, the Schwarzschild radius, the boundary where escape velocity equals the speed of light. Cross this line, and nothing can save you. Not rocket engines, not exotic physics, not any force known to science. You're gone. For a black hole, size equals mass. The more massive the black hole, the larger its event horizon. The central monster contains 4 million solar masses, which translates to a Schwarzschild radius of about 12 million kilometers. Double that for the diameter, and you get 14 million miles. Put that in perspective. The distance from Earth to our home star is 93 million miles. The event horizon spans roughly 15% of that distance. If you placed the black hole at the center of our solar system, its event horizon would extend well past Mercury's orbit, reaching about halfway to Venus. Inside the event horizon, spacetime itself flows toward the singularity faster than light can travel outward. It's not that gravity pulls too strongly to escape. It's that every direction you can travel points toward the center. There is no outward path. The future direction of time points inward, and you cannot move backward in time any more than you can stop aging. The event horizon is not a physical surface. You wouldn't hit a wall or feel resistance crossing it. For an outside observer, you'd appear to slow down, redshift, and fade away as you approached, never quite reaching it in finite time. But from your perspective, you'd cross smoothly, noticing nothing special at the exact moment of crossing. That's the terrifying part. The event horizon doesn't announce itself, no warning signs, no sudden change in physics. One moment you're outside, theoretically capable of escape if you had enough thrust. The next moment you're inside, and escape becomes impossible regardless of what you do. Tidal forces at the event horizon depend on the black hole's mass. For supermassive black holes like this one, the tidal forces at the horizon are relatively mild. You could cross the event horizon and survive, at least briefly. The stretching would be uncomfortable, but not immediately lethal. Compare that to a stellar mass black hole, maybe 10 times the mass of our home star. Its event horizon would be tiny, only about 40 miles across. The tidal forces at that horizon would be astronomical, ripping apart anything that approached. You'd be spaghettified long before crossing. But survival at the event horizon doesn't mean survival inside. Once past the horizon, you have hours at most before reaching the singularity, and during those hours, tidal forces grow stronger. What was mild at the horizon becomes violent deeper in. Eventually, you get stretched and compressed beyond any material's breaking point. The event horizon also marks a boundary for information. Anything that crosses cannot send signals back out. This creates the black hole information paradox, one of the deepest puzzles in theoretical physics. Astronomers have now imaged the event horizon. The Event Horizon Telescope, a global network of radio dishes working together, captured the shadow of the black hole against the glowing accretion disk. The image shows a dark circle surrounded by a bright ring of light. The dark circle is slightly larger than the event horizon because light rays can orbit the black hole just outside the horizon before escaping or falling in. That image confirms the size, 14 million miles. Exactly what general relativity predicts for a 4 million solar mass black hole. But the event horizon is not the only boundary worth noting. Just outside it, matter doesn't fall in, it orbits. And that orbiting matter creates something spectacular. Not everything falls in. Some matter gets ejected, accelerated to velocities approaching the speed of light, and fired into space like a cosmic bullet. These are the jets, and they're among the most powerful phenomena in the universe. The central black hole doesn't currently produce strong jets. It's too starved, accreting matter too slowly to power the massive outflows seen in active galaxies. But evidence suggests it had jets in the past, and the physics that creates jets elsewhere applies here too. Jets form in the region just outside the event horizon. As matter spirals inward through the accretion disk, magnetic fields thread through the plasma. These fields get twisted and amplified by the disk's rotation, building up magnetic pressure. Eventually, that pressure launches material perpendicular to the disk, creating twin jets pointing in opposite directions along the rotation axis. The acceleration is violent. Matter goes from orbital velocities to relativistic speeds in a matter of light hours. Magnetic fields act like rails, channeling the plasma and preventing it from spreading out. The jets stay collimated, narrow beams of particles traveling in nearly straight lines across vast distances. The energy comes from the black hole's rotation. As matter falls in, it transfers angular momentum to the black hole, making it spin faster. But that rotation can also be extracted. Magnetic field lines, connecting the black hole to the accretion disk, act like a dynamo, converting rotational energy into electromagnetic energy that powers the jets. This process, called the Blandford-Znajek mechanism, can tap up to 29% of a black hole's mass energy. For a supermassive black hole, that's enough power to outshine the entire galaxy. Active galactic nuclei powered by accreting black holes can produce jets extending millions of light years into intergalactic space. The jets don't just carry matter, they carry energy and momentum. When a jet slams into the surrounding interstellar medium, it creates shock waves. These shocks heat the gas, ionize atoms, and trigger secondary emissions across the electromagnetic spectrum. Particles in the jets reach extreme energies. Electrons and protons get accelerated to velocities so close to light speed that their kinetic energy dwarfs their rest mass. These ultra-high energy particles become cosmic rays when they eventually escape the jet and travel through space. Observations of other galaxies show jets in action. M87, a giant elliptical galaxy 55 million light-years away, has a jet extending 5,000 light-years from its central black hole. The jet is visible in radio, optical, and X-ray wavelengths, glowing from synchrotron radiation as electrons spiral in magnetic fields. The galactic center once had similar jets, bubbles of hot gas extending above and below the galactic plane, called the Fermi bubbles, likely formed from past jet activity. These bubbles span 50,000 light-years, filled with gamma-ray emitting plasma that was injected there millions of years ago when the black hole was more active. The bubbles prove the central monster isn't always quiet. There have been periods, perhaps triggered by major accretion events, when the black hole flared up and powered jets. Those episodes reshaped the galactic center, evacuating gas and injecting energy into the surrounding halo. Today, only weak outflows persist. Radio observations detect faint jets extending a few light-years from the center, much smaller than the jets in active galaxies. These weak jets barely affect their surroundings, carrying away only a tiny fraction of the energy available. But the potential for stronger jets remains. Feed the black hole more matter, and it could roar back to life. A large gas cloud falling in, or a star being disrupted, could trigger a temporary burst of jet activity. When that happens, the galactic center would light up in ways we've only seen in distant, active galaxies. The jets aren't the only thing the accretion flow produces. Where matter piles up, waiting to fall in, it creates a disk that outshines everything around it. The disk is where matter dies. Not quickly, not cleanly, but slowly, violently, releasing every ounce of energy it possesses before finally crossing the event horizon. This is the accretion disk, and it's the brightest thing in the galactic center despite being only light hours across. Matter doesn't fall straight into a black hole. It has angular momentum, residual rotation inherited from the larger structures it came from. That rotation prevents direct infall. Instead, the matter settles into a swirling disk, orbiting the black hole while gradually spiraling inward. Friction does the work. As gas orbits at different speeds depending on distance from the central object, adjacent layers rub against each other. This friction converts orbital energy into heat. The gas heats up. The hotter it gets, the more it radiates. By the time matter reaches the innermost stable orbit, it's glowing white-hot in visible light and blazing in X-rays. The temperature peaks in the inner disk. Close to the black hole, gas reaches millions of degrees. At those temperatures, atoms are fully ionized. Electrons rip free from nuclei, creating a plasma that's more than 99% empty space. The few collisions that do occur release high-energy photons. The disk is relatively dim because the accretion rate is low. Only about 1/10,000th of a solar mass falls in per year. Compare that to active galactic nuclei, which can accrete several solar masses per year. Those systems have accretion disks bright enough to outshine their entire host galaxies. But even a dim accretion disk produces significant radiation. Radio waves from the cooler outer regions, infrared from the warm mid-disk, optical and ultraviolet from the hot inner disk, X-rays from the hottest zones just outside the event horizon. The spectrum spans nearly every wavelength we can observe. The disk is turbulent. Magnetic fields thread through the plasma, creating instabilities that generate fluctuations in density and temperature. These fluctuations cause the emission to vary on timescales of minutes to hours. Monitoring this variability reveals the disk's structure and dynamics. Gas in the disk doesn't just orbit, it also moves inward and outward, creating complex flow patterns. Some gas gets flung outward by magnetic pressure, escaping the system entirely. Other gas loses energy and spirals inward, eventually crossing the event horizon. The innermost stable circular orbit marks a critical boundary. Inside this radius, there are no stable orbits. Gas reaching this point must either fall into the black hole within a few orbits or be ejected. For the central black hole, the innermost stable orbit sits at about 3 times the Schwarzschild radius, roughly 42 million kilometers from the center. Gas inside the innermost stable orbit plunges inward rapidly. It doesn't have time to radiate away all its energy. This is called advection-dominated accretion, and it makes the very inner disk less luminous than you'd expect. The gas is hot, but it falls in so fast it carries most of its heat across the event horizon rather than radiating it. The disk also contains magnetic fields strong enough to matter. These fields transport angular momentum outward, allowing matter to move inward. Without this magnetic transport, friction alone couldn't move gas inward fast enough. Disks around black holes come in different flavors. Thick disks, thin disks, advection-dominated flows. Which type forms depends on the accretion rate. The central black hole currently has an advection-dominated flow, hot and puffy rather than thin and flat. The disk's glow isn't uniform. Hotspots form where magnetic instabilities concentrate energy. These hotspots orbit the black hole, creating periodic brightness variations as they swing in and out of view. Tracking these variations lets astronomers map the disk's structure in detail. But the disk does more than just glow. The intense gravity near the black hole bends light in ways that create optical illusions. Reality bends. Light traveling near the central black hole doesn't move in straight lines. The monster's gravity warps spacetime so severely that photon paths curve dramatically. A single star behind the black hole can appear in multiple locations simultaneously. One object becomes 2, 3, or even more images scattered across the sky. This is gravitational lensing, predicted by Einstein and observed throughout the universe. But near the galactic center, the effect reaches extreme levels. The bending isn't subtle. Light rays can curve by tens of degrees, creating distortions visible with current telescopes. The Einstein ring represents perfect alignment. When a background star, the black hole, and Earth line up exactly, the star's light spreads into a complete ring around the black hole. This ring has a specific radius, determined by the black hole's mass and the geometry of the system. For the central object, the Einstein radius is about 50 microarcseconds, barely resolvable with the most powerful instruments. Most of the time, alignment isn't perfect. Instead of a full ring, you see arcs or multiple point-like images. The background star appears stretched, duplicated, or distorted depending on how close the alignment is. These images have different brightnesses because the lensing magnifies light along different paths by different amounts. Strong lensing occurs closest to the black hole. Stars passing directly behind would be lensed so strongly that their images wrap around multiple times. One star could generate 4 or 5 distinct images, each following a different curved path through spacetime. The lensing isn't static. As stars move in their orbits, the geometry changes continuously. Images brighten and dim. Multiple images appear and disappear. The pattern evolves in real time, creating a dynamic light show detectable with careful monitoring. Microlensing events happen when a foreground star passes in front of a background star. The foreground star's gravity acts as a lens, temporarily brightening the background star. These events are rare but observable. Several microlensing events have been detected toward the galactic center, revealing the presence of faint stars and stellar remnants that would otherwise be invisible. The lensing also affects the accretion disk. Light from the backside of the disk gets bent up and over the black hole, becoming visible when it otherwise wouldn't be. This means we see both the front and back of the disk simultaneously. The Event Horizon Telescope image shows this effect, with the bright ring containing light from multiple parts of the disk superimposed. Gravitational lensing magnifies distant objects. A galaxy far behind the galactic center would appear brighter and larger due to lensing by the central mass. This magnification makes it easier to study distant objects that would otherwise be too faint. Astronomers use this technique to probe the early universe. Relativistic beaming adds another complication. Matter moving toward us at relativistic speeds appears brighter than matter moving away due to Doppler boosting. Combined with gravitational lensing, this creates asymmetries in the observed emission. Time delay is the final piece. Light, taking different paths around the black hole, arrives at different times. A sudden flare in the accretion disk would be seen multiple times, with delays ranging from minutes to hours depending on the path length difference. Monitoring these time delays provides information about the black hole's mass and spin. But lensing is just one way the black hole's rotation affects light. The spinning mass drags spacetime itself, creating effects that shouldn't exist in a non-rotating universe. Spacetime rotates. Not metaphorically, literally. The central black hole spins, and that spin drags spacetime around with it. Stand still near the black hole, and you'd find yourself rotating whether you wanted to or not. The fabric of the universe itself is being pulled into orbital motion. This is frame dragging, also called the lens-Thering effect, after the physicists who first calculated it. Every rotating mass does this, including Earth. Our planet's rotation drags spacetime around it by a tiny amount, about 1 part in a few trillion. Precision measurements with the Gravity Probe B satellite confirmed it in 2011. Near the galactic center, frame dragging is 1,000,000 billion times stronger. The black hole rotates, possibly close to the maximum rate allowed by physics. That rotation creates a region called the ergosphere, a zone outside the event horizon where nothing can remain stationary. Even light trying to hover in place gets dragged into orbital motion. The ergosphere extends farther from the black hole than the event horizon, especially near the equator. Its boundary is the static limit, the surface where the dragging of spacetime equals the speed of light. Cross the static limit inward, and you must orbit. There's no choice. Standing still becomes as impossible as traveling faster than light. Inside the ergosphere, you can still escape. You're not past the event horizon yet, but you must move, and that motion must include a component in the direction of the black hole's rotation. You can fight against the inward pull of gravity and escape to infinity. but you cannot stop rotating. The Penrose process exploits the ergosphere to extract energy from the black hole. Drop an object into the ergosphere and split it into two pieces at just the right moment. One piece falls into the black hole with negative energy relative to the rotating spacetime. The other piece escapes with more energy than the original object had. You've stolen rotational energy from the monster. This process is theoretical for now, but it could power natural phenomena. Jets might be extracting rotational energy through the Penrose process, mediated by magnetic fields. The energy comes from slowing the black hole's rotation, converting spin into outward moving matter. Frame dragging also affects orbits. Objects orbiting near the black hole don't follow simple Keplerian paths. Their orbital planes precess, tilting and rotating as spacetime itself rotates beneath them. This precession is measurable for the stars, providing another test of general relativity. The precession rate depends on the black hole's spin. A non-rotating black hole produces no frame dragging. A maximally rotating black hole drags spacetime so strongly that orbits near the event horizon precess dramatically. By measuring precession rates, astronomers can determine how fast the central object spins. Current estimates suggest moderate rotation, maybe 50 to 90% of the maximum, not slowly like some black holes, but not at the theoretical limit either. This spin rate affects the size of the ergosphere and the efficiency of energy extraction processes. The spin also affects the innermost stable orbit. For a non-rotating black hole, this orbit sits at 3 Schwarzschild radii. For a maximally rotating black hole, it can be as close as 1 Schwarzschild radius, depending on whether the orbit is prograde or retrograde. Closer stable orbits mean matter can get hotter before falling in. Frame dragging warps not just trajectories but time itself. Clocks orbiting in the direction of the black hole's rotation tick at different rates than clocks orbiting against it. The difference is small but measurable, another subtle test of general relativity that observations continue to confirm. But frame dragging is gentle compared to what happens when you get even closer, when tidal forces stop pulling and start ripping. Matter surrenders. You're approaching the innermost regions, where tidal forces reach levels that nothing can resist. Even the electromagnetic bonds holding atoms together start failing. Molecules tear apart. Atoms separate into nuclei and electrons. Structure at every scale collapses. The tidal force equation is simple. The difference in gravitational pull between 2 points increases with the inverse cube of the distance from the mass. Get close enough to any massive object, and that difference becomes destructive. For a human falling feet first toward the black hole, tidal forces would become uncomfortable around the innermost stable orbit. Your feet, slightly closer to the gravitational source, would be pulled harder than your head. The difference would create a stretching sensation, like being on a medieval rack. Move closer, and discomfort becomes pain. The forces pulling your feet downward and your head upward increase exponentially. Your spine compresses. Your limbs stretch. Blood struggles to flow against the differential pull. At some point, your body loses structural integrity. The breaking point for human tissue occurs well outside the event horizon. You'd be torn apart before reaching the point of no return. For stellar mass black holes, this happens even farther out. Tidal disruption can occur at distances of hundreds of Schwarzschild radii from smaller black holes, but the central supermassive black hole is different. It's massive enough that tidal forces at the event horizon are relatively mild. You could cross the horizon intact. Spaghettification doesn't begin immediately. You'd have minutes, possibly hours, before tidal forces grew strong enough to destroy you. Those minutes would be terrifying. The tidal gradient increases as you fall deeper. What was manageable at the horizon becomes intolerable closer in. Your body elongates. Compression forces squeeze you perpendicular to the direction of fall. The medical term for this torture doesn't exist because no one has experienced it and survived to name it. atoms themselves eventually fail. At extreme tidal gradients, the electromagnetic forces binding electrons to nuclei can't compete with gravity's differential pull. Atoms ionize, electrons strip away. What was once matter with chemical properties becomes a plasma of separate charged particles. Even nuclei might not survive. At close enough proximity to the singularity, tidal forces could overcome the strong nuclear force holding protons and neutrons together. Nuclei would disintegrate into their constituent quarks. Matter as we know it would cease to exist in any recognizable form. The exact sequence of destruction depends on what's falling in. A star approaching too close gets disrupted in a tidal disruption event. The star stretches into a long stream of gas, half of which falls into the black hole while half gets flung outward at high velocity. The infalling material creates a bright flare as it heats up and radiates. Several tidal disruption events have been observed around supermassive black holes in other galaxies. They appear as sudden brightenings lasting weeks to months, much more luminous than the black hole's normal emission. The light curve and spectrum match theoretical predictions for stellar disruption, confirming our understanding of tidal forces. Planets would fare even worse. Less gravitationally bound than stars, they'd be shredded at greater distances. A Jupiter-sized planet approaching would disintegrate outside the innermost stable orbit, creating a debris cloud that slowly accretes. Smaller objects like asteroids or spacecraft would be torn apart even farther out. The threshold depends on the object's density and tensile strength. Dense, rigid structures resist tidal forces better than loose aggregates. But no material is infinitely strong. Push close enough, and everything breaks. The universe has an absolute limit on how much stress matter can withstand, set by the properties of atomic and nuclear forces. Near the singularity at the black hole's core, those limits are exceeded by astronomical margins, and from outside, watching an object fall toward that fate reveals one of the strangest effects in all of physics. Watch something fall toward the event horizon, and you witness infinity. Not literally infinite time, but something approaching it. The object appears to slow down as it nears the black hole. Its motion becomes sluggish. The descent that should take seconds stretches into minutes, then hours, then days. Eventually, the object seems to freeze completely, hovering just above the event horizon forever. This is gravitational time dilation taken to its extreme. Time near the event horizon runs so much slower than time far away that the difference becomes dramatic. An object falling toward the black hole experiences time normally from its own perspective, but to a distant observer, that object's clock appears to tick slower and slower as it approaches the horizon. The mathematics are precise. Time dilation factor depends on the Schwarzschild radius and the distance from the black hole. As distance approaches the Schwarzschild radius, the time dilation factor approaches infinity. 1 second on the falling object's clock corresponds to hours, then years, then millennia on the distant observer's clock. Light from the falling object gets redshifted. Photons climbing out of the deepening gravitational well lose energy. Their wavelengths stretch toward the red end of the spectrum, then into infrared, then into radio waves. Eventually, the wavelength becomes so long that detecting the photons becomes impossible with any realistic instrument. The object also dims. Photons emitted at a steady rate from the falling object's perspective arrive at the distant observer at an ever-decreasing rate due to time dilation. Fewer photons per second means lower brightness. Combined with the redshift, the object fades from view rapidly as it approaches the horizon. From the falling object's perspective, none of this happens. The trip to the event horizon takes finite time measured by the object's own clock. Seconds tick normally. The object crosses the horizon smoothly, without noticing anything special about that particular location. The universe outside appears to speed up, blue shifted and brightened, but otherwise, physics proceeds as expected. This asymmetry creates a paradox. The outside observer never sees the object cross the horizon. It appears frozen forever just above. But the falling object crosses in finite proper time and continues inward. Both perspectives are valid within their own reference frames, yet they describe completely different outcomes. This leads to the frozen star interpretation. From outside, infalling matter accumulates just above the event horizon, forming a thin shell of frozen material. The black hole appears not as a void but as a dense surface of matter compressed to extreme densities, approaching but never quite reaching the horizon. But that interpretation fails when you consider the falling object's perspective. From that viewpoint, the horizon is crossed and matter does enter the black hole. The horizon is real, not an asymptotic limit. Both descriptions are correct in their respective frames, a consequence of relativity's insistence that there's no preferred reference frame. The time dilation also affects what the falling observer sees. Looking back toward the outside universe, they'd witness time speeding up. Stars would evolve rapidly. The galaxy would age before their eyes. In the final moments before crossing the horizon, they'd see the entire future history of the universe flash past, compressed into seconds by the extreme time dilation. Or would they? The calculation is tricky. Light from the future universe has to catch up to the falling observer, and some of it never does. The observer might see time accelerate but not reach infinity. Communication becomes impossible. Radio signals sent from just above the event horizon take longer and longer to reach distant observers. Eventually, the delay becomes so extreme that the signal effectively never arrives. The falling object becomes causally disconnected from the outside universe well before physically crossing the horizon. But the black hole doesn't just trap light trying to escape. It also produces light through a quantum process that shouldn't exist according to classical physics. The black hole evaporates. Slowly, unimaginably slowly, but it happens. The central monster is leaking particles from its event horizon through a quantum process discovered by Stephen Hawking in 1974. The radiation is real, predicted by combining quantum mechanics with general relativity, and it means black holes aren't truly black. The mechanism is subtle. Quantum field theory says empty space isn't truly empty. Virtual particle pairs constantly pop into existence and annihilate each other everywhere in the universe. These pairs exist for such brief moments that they don't violate conservation of energy, borrowing their mass from quantum uncertainty and paying it back before anyone notices. But near the event horizon, something changes. When a virtual pair appears right at the horizon, one particle can fall into the black hole while the other escapes. The escaping particle becomes real, no longer virtual, because its partner is gone. That particle carries energy away from the black hole. Where does the energy come from? The black hole itself. Each escaping particle reduces its mass by a tiny amount. The black hole pays the energy cost, and over time, this payment adds up. The monster shrinks. The temperature of Hawking radiation depends inversely on the black hole's mass. Smaller black holes are hotter. Stellar mass black holes have temperatures of billionths of a degree above absolute zero. The supermassive black hole at the galactic center, with 4 million solar masses, has a temperature of about 15 trillionths of a degree. That's cold. Colder than the cosmic microwave background, which sits at roughly 3 degrees above absolute zero. This means the central object currently absorbs more energy from the background radiation than it emits through Hawking radiation. The black hole is growing, not shrinking, because the universe around it is warmer than it is. But the universe is cooling. The cosmic background temperature drops as space expands. Eventually, in the far future, the background will cool below the Hawking temperature of even supermassive black holes. When that happens, the galactic center's black hole will start losing mass through Hawking radiation faster than it gains mass through accretion. the evaporation accelerates. As the black hole loses mass, its temperature increases. Higher temperature means more rapid evaporation. The process feeds itself, creating a runaway effect. The final moments of a black hole's life release enormous energy as the temperature spikes and particles stream away in a flood. For the central monster, this final evaporation lies inconceivably far in the future. The timescale for a black hole to evaporate through Hawking radiation scales with the cube of its mass. It will take approximately 10 to the power of 100 years to evaporate completely. That's a 1 followed by 100 zeros, far longer than the current age of the universe. But the radiation exists now, even if we can't detect it. Photons with wavelengths, measured in light years, trickle away from the event horizon at a rate so slow that the black hole loses less than 1 atom's worth of mass per year. Detecting this emission against the background of other radiation sources is impossible with current technology. Hawking radiation raises profound questions. The radiation appears thermal, meaning it carries no information about what fell into the black hole, but quantum mechanics says information cannot be destroyed. This creates the black hole information paradox, one of the deepest unsolved problems in theoretical physics. Does information somehow escape in subtle correlations in the Hawking radiation? Does it get preserved inside the black hole somehow? Does it get destroyed, forcing us to modify quantum mechanics? Physicists have debated these questions for decades without reaching consensus, and that paradox reveals something strange about the nature of reality itself. The universe has a problem. Two of our most successful theories contradict each other at the event horizon. General relativity says information falling into a black hole is lost forever, trapped behind the horizon where it can never escape. Quantum mechanics says information cannot be destroyed under any circumstances. Both theories have been tested extensively. Both appear correct, yet they cannot both be right about black holes. Information, in physics, means more than knowledge. It's the complete specification of a quantum state. Every particle, every field, every property that could be measured about a system. Quantum mechanics insists this information is preserved as systems evolve. You can scramble it, spread it out, encode it in complex ways, but you cannot destroy it. Black holes seem to violate this principle. Throw an encyclopedia into the central black hole, and it crosses the event horizon and disappears. From the outside, you can measure the black hole's mass, charge, and spin. Those 3 numbers completely describe it. No Hare theorem says that's all the information a black hole carries. Everything else is gone. But the encyclopedia contained vastly more information than just its mass. The text, the molecular structure, the quantum states of every atom. All that information exceeds the 3 numbers describing the black hole by astronomical factors. Where did it go? Hawking radiation doesn't help. The radiation appears thermal, meaning it's random and carries no information about what created it. A black hole formed from encyclopedias produces the same Hawking radiation as one formed from hydrogen gas, as long as the masses match. The radiation seems to destroy information just as thoroughly. This creates a paradox. Start with a pure quantum state, like a specific encyclopedia. Let it collapse into a black hole. Wait for the black hole to evaporate through Hawking radiation. You're left with thermal radiation, a mixed state, not a pure state. Information has been lost. Quantum mechanics says this cannot happen, yet the calculation appears airtight. Proposed solutions abound, none fully satisfactory. Maybe information does escape in subtle correlations in the Hawking radiation. The radiation isn't truly thermal, but contains microscopic encoded data that preserves the information. Extracting that information would require impossibly precise measurements, but in principle, it exists. Maybe the information gets released in the final burst of evaporation. The last moments of a black hole's life might be governed by unknown quantum gravity effects that preserve and release the trapped information. We can't calculate this regime without a complete theory of quantum gravity. Maybe the information never enters the black hole. The holographic principle suggests all information about a black hole's interior is encoded on its event horizon. Nothing actually falls in. Everything that appears to cross the horizon is really a holographic projection, with the true information stored on the surface. Maybe the information is preserved, but becomes inaccessible. If you fall into the black hole to retrieve the information, you can never communicate it back out. The information exists, but becomes causally disconnected from the outside universe. This doesn't violate quantum mechanics in the strictest sense, but feels like cheating. The paradox has driven decades of research in quantum gravity. String theory, loop quantum gravity, and other approaches all attempt to resolve it. Each offers partial insights, but no complete solution that everyone accepts. The recent resolution, proposed by Hawking himself before his death, suggests information does escape through radiation, but the calculation requires including quantum effects near the horizon that earlier analyses ignored. These effects create subtle correlations between early and late radiation that preserve unitarity, but proving this requires understanding quantum mechanics in curved spacetime, a regime where we lack experimental data. We cannot build black holes in laboratories. We cannot send probes into the central monster to measure what happens at the horizon. The paradox matters because it probes the intersection of quantum mechanics and gravity. Solving it likely requires understanding quantum gravity, the theory that should describe how space and time behave at the smallest scales. That theory would unify physics. Yet, even without solving the paradox, we know something stranger exists. A shell where light cannot escape but also cannot fall in. Light orbits forever, not spiraling in, not escaping, just circling endlessly at a fixed radius around the black hole. This is the photon sphere, and it exists at precisely 1.5 times the Schwarzschild radius. For the central monster, that's about 21 million kilometers from the center. At this exact distance, space-time curvature equals the centrifugal effect needed to keep photons in circular orbits. Light traveling tangent to the sphere follows a closed loop. It returns to its starting point after completing one orbit, then does it again and again, forever, unless something disturbs it. The orbit is unstable. Any tiny perturbation sends the photon either inward toward the black hole or outward into space. No mechanism exists to correct deviations. The photon sphere is like balancing a pencil on its point, theoretically possible but practically impossible to maintain. This instability means the photon sphere isn't filled with light. Photons don't accumulate there. Any photon reaching the sphere almost immediately gets nudged, one way or the other, and departs. The sphere exists as a mathematical surface, a boundary in space-time where circular light orbits are possible, not as a physical shell glowing with trapped light. But the photon sphere affects what we see. It marks the outer edge of the black hole's shadow. Light rays passing inside the photon sphere get captured and spiral into the black hole. Light rays passing outside can escape to infinity. The boundary between these regions creates the dark circle we observe in event horizon telescope images. The shadow is larger than the event horizon. The photon sphere sits 50% farther from the center than the horizon. This means the dark region we see extends beyond the actual point of no return. The black hole appears larger than it truly is, because light gets captured before reaching the horizon. Photons orbiting at the photon sphere experience extreme time dilation and gravitational blue shift. To a distant observer, the orbiting light appears to freeze in time and shift to higher energies. These effects create the bright ring visible in black hole images, where light from the accretion disk gets amplified and distorted. Multiple orbits are possible. A photon could circle the black hole once, twice, 3 times, or more before escaping or falling in. Each additional orbit creates a thinner, dimmer ring in the image. The Event Horizon Telescope resolved the primary ring but not the higher order ones, which are too faint and narrow for current instruments. The photon sphere also explains why black holes appear black. Any light emitted from inside the photon sphere cannot escape. It either gets trapped in unstable orbits that quickly decay inward, or it heads directly toward the event horizon. No stable paths lead outward. The region becomes a one-way trap for radiation. For rotating black holes, the photon sphere splits into multiple surfaces depending on the direction of light's orbit. Prograde orbits, moving in the same direction as the black hole's rotation, have a different critical radius than retrograde orbits. Frame dragging affects photon trajectories, changing where stable circular orbits can exist. The photon sphere demonstrates how drastically gravity can affect light. In weak gravitational fields, light travels in nearly straight lines with tiny corrections. Near black holes, the corrections dominate. Light follows paths so curved they loop back on themselves. This has practical implications for observing the galactic center. When we point telescopes at this region, some of the light we detect has taken bizarre paths, circling partway around the black hole before escaping. But the photon sphere is still outside the point of no return. Cross the event horizon, and stranger things await. Things that rip matter apart at scales smaller than atoms. Atoms die here. Not molecules, not cells. Atoms themselves, the fundamental units of matter, get torn apart by forces so extreme that chemical bonds become irrelevant. You're inside the event horizon now, falling toward the singularity, and the universe is ripping you to pieces one layer at a time. Spaghettification starts gently. The tidal gradient pulls your feet harder than your head. The difference creates stretching along your body's length and compression perpendicular to it. You elongate like clay on a potter's wheel, drawn into a thinner and thinner strand. The stretching accelerates. What was uncomfortable becomes agonizing. Your bones crack under the strain, muscles tear, blood vessels rupture. Your body loses structural integrity and begins to separate into chunks. But even that grotesque process is just the beginning. Molecules break next. The hydrogen bonds holding proteins together snap under the relentless pull. Complex organic molecules fragment into simpler compounds. Water molecules dissociate into hydrogen and oxygen. The chemical machinery of life disintegrates into its components. You're no longer a body, you're a stream of molecular fragments. Then the molecules themselves fail. Carbon-carbon bonds, among the strongest in chemistry, break under tidal stress. Long molecular chains fragment into smaller pieces, benzene rings split apart. The concept of chemical structure stops meaning anything because forces that should be immutable are being overwhelmed. Individual atoms feel the pull. The nucleus, at the atom's center, experiences different gravity than the electron cloud surrounding it. In normal circumstances, electromagnetic forces binding electrons to nuclei are vastly stronger than gravity. But tidal forces scale with proximity to the singularity, and electromagnetic forces don't. At extreme tidal gradients, gravity wins. Electrons get stripped from atoms by differential gravitational pull. Ionization occurs not because of heat or electromagnetic fields, but because spacetime itself is so warped that different parts of an atom experience measurably different gravitational forces. Matter becomes plasma by gravitational fiat. Even the plasma phase doesn't last. Closer to the singularity, the tidal gradient continues growing. Atomic nuclei themselves face destruction. Protons and neutrons, bound together by the strong nuclear force, are pulled apart. The strong force is the most powerful in nature, operating over distances measured in femtometers. But tidal forces can exceed even the strong force near the singularity. Nuclei disintegrate into individual protons and neutrons. Those particles, in turn, get stretched. Protons and neutrons aren't fundamental. They're made of quarks held together by gluons. At close enough proximity to the singularity, even those bonds break. Matter dissolves into a quark-gluon plasma, the same state that existed microseconds after the Big Bang. But the singularity tolerates no structure. Quarks themselves might be torn apart if they have internal structure we haven't discovered. The universe peels away every layer of organization, reducing complexity to its absolute minimum. What was once you becomes a stream of fundamental particles falling toward infinite density. The timescale for this destruction depends on where you started. Fall across the event horizon of the supermassive black hole, and you have hours before reaching the singularity. During that time, tidal forces grow from negligible to overwhelming. The spaghettification is gradual. For smaller black holes, the process is faster. Cross the event horizon of a stellar mass black hole, and you have milliseconds before hitting the singularity. The tidal forces at the horizon of such black holes are already lethal. The mathematical description is precise. The Riemann curvature tensor measures tidal forces. Near the singularity, components of this tensor diverge to infinity. Infinite tidal force means infinite stretching and compression. No material, no structure, nothing survives. But infinity is where mathematics breaks. Where equations produce infinities, physics admits ignorance. The singularity represents the edge of our knowledge. And beyond that edge, where the singularity waits, our understanding of reality collapses entirely. The singularity defies everything. Infinite density, infinite curvature, zero volume. These aren't approximations or exaggerations. They're what general relativity predicts when you extend the equations all the way to the black hole's center, and infinity is where physics breaks down completely. Infinite density means the mass of 4 million stars compressed into a point with no size. Not very small. Actually, zero. All that matter occupying no space whatsoever. The concept violates intuition because it violates the assumptions underlying our physical theories. General relativity predicts this singularity, but also signals its own failure by doing so. When equations produce infinities, they're telling us they've been pushed beyond their domain of validity. The theory works magnificently everywhere else, from Mercury's orbit to gravitational waves from colliding black holes. But at the singularity, it admits defeat. What actually exists there? Nobody knows. Quantum mechanics should matter when you compress mass to such extreme densities. At some point, quantum effects must prevent the collapse to infinite density, but we don't have a theory that combines quantum mechanics with general relativity successfully. Quantum gravity remains unsolved. String theory suggests the singularity might be replaced by a tiny but finite structure. Strings and branes operating at the Planck scale around 10 to the negative 35 meters across. At those scales, space and time might not be continuous but discrete, preventing the truly infinite compression. Loop quantum gravity offers different predictions. Space itself might come in indivisible chunks. You cannot compress matter beyond the Planck density, roughly 10 to the 94 grams per cubic centimeter. When that density is reached, quantum effects halt the collapse, creating a region of extremely high but finite density. But these are speculations. We cannot test them experimentally. We cannot probe conditions inside black holes. Everything that crosses the event horizon is lost to observation. Even in principle, no signal can escape to tell us what's happening inside. The singularity might not be a point. For rotating black holes, the singularity is predicted to be a ring. The ringularity, as it's called, is a circle of infinite density spinning inside the event horizon. Matter falling in might pass through the ring rather than hitting it, entering regions of spacetime with bizarre properties. Those regions include closed time-like curves, paths through spacetime that loop back on themselves. Follow such a curve, and you'd return to your own past. This allows time travel in theory. Though whether such paths actually exist inside real black holes is unclear. The mathematics allows them, but physics might forbid them. Naked singularities are even stranger. The cosmic censorship hypothesis says singularities must always be hidden behind event horizons. Nature abhors naked singularities, but we have no proof this hypothesis is true. If naked singularities exist, they'd create regions where our physical laws fail, but from which light could escape. We could observe the breakdown of physics directly. No naked singularities have been observed. Every singularity we know about is cloaked by an event horizon. But that could be selection bias. The singularity also represents a boundary in time, not just space. General relativity predicts spacetime itself terminates at the singularity. Time doesn't continue beyond. There is no after because time stops existing. The notion of asking what happens next becomes meaningless when next doesn't exist. This has profound implications for the nature of reality. If spacetime can begin at the Big Bang and end at singularities, then space and time are not fundamental. They emerge from something deeper, something our current theories don't describe. Finding that deeper layer is one of the greatest challenges in theoretical physics. The singularity at the center of the galactic black hole will likely remain forever beyond our reach. We cannot visit it. We cannot receive signals from it. We can only infer its existence from the behavior of matter outside the event horizon and trust that our equations, pushed to their limits, are pointing toward something real. 4 million solar masses, compressed to infinite density, the gravitational anchor of our galaxy, the endpoint of matter's journey into the ultimate unknown. This is where the impossible becomes real, where 26,000 light-years of cosmic descent finally leads, to a place where physics surrenders and mystery takes over, the center of the galaxy, where everything ends and nothing escapes.